And howdy there, Calculus 2 students. Today what we're going to do is take the techniques that we have learned in this chapter and kind of combine them together and maybe go a little further with those techniques. In this first example, we have something where we're supposed to take the limit as x goes to 0. However, if you were to try to find this actual limit, you see that you have a 0 over 0 indeterminate form, which means that we could use L'Hopital's rule. If you did this, you would actually have to use L'Hopital's rule 4 times. So what we're going to do, and we could do that to get the limit, what we're going to do instead though is we're going to use the Maclaurin series that we found in section 10.3, and this is an approximate for our cosine x, so we're going to substitute that in directly for cosine x and see if we can get our limit in that way. So let me write that down. And here's what that substitution looks like, and we have a little simplifying that we can do. If you'll notice, this x squared term right here will drop out because when I multiply this 2 times this term here, I will have x squared minus x squared. So these terms will drop. Notice also that this will be 2 minus 2, so this term and this 1 will also drop, leaving me with just this x to the 4th, blah blah blah, all over 3x to the 4th. So in simplifying that, let's see what we get. In simplifying this even further, you'll see that I get that the limit is 1 over 36. Now that was fairly straightforward by using this approximation that we got previously. Now it wasn't necessarily easy to get this approximation because we did this in the previous section, but once we have it, we might as well use it, and it makes finding this limit a lot easier. This is another messy limit to deal with. And I like to play the same game with this sign because I did have this this Taylor series centered at 0 that I got in a previous section in 10.3. So I'd like to use that, but I can't really use it with this x going to infinity, so let's instead replace x with, we're going to replace x with 1 over t, and that way as x goes to infinity, we can say that t approaches 0 from the right, and we're going to replace our x's with those t's, and then we're going to replace that sign with this Taylor series. So we'll write that down. What's up now is just replacing our x with 1 over t and simplifying that to see what it looks like. Next up, we will be replacing sine t with this Taylor series approximation, and we'll see what we get from there. And after simplifying, you'll see that this one fell out similarly to the previous example. So it made these limits, finding these limits, much easier. In this next example, we are to differentiate our Maclaurin series, our approximation for sine x, and see if this approximation equals this Maclaurin series for cosine x. So in finding f prime of x for this one, that's going to be a 1 minus 3x squared over, and that will be 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial, and so forth. In simplifying this, you will see that if I wrote out the factorial, 3 times 2 times 1, the 3 would cancel, leaving me with 2 factorial. This is 5 times 4 times 3 times 2 times 1. The 5's cancel, leaving me with 4 factorial, so I'll write that a little neater. Alright, and if you'll notice, voila, that is the Maclaurin series approximation for cosine, and it sure does work. In our next example, we are to find the solution to the given differential equation, and we're going to use Taylor series to do this. So if we expand this about 0, and we know that our solution will be some form that has this particular sum, then all we have to do is figure out these coefficients, and then we'll be able to figure out the power series for the Taylor. Alright, so first thing, let's substitute the initial condition into the power series and see what we get. In substituting this in, we find that our first constant is 6. Now we need to get the rest of these constants, and so let's look at y prime of 0 and note that it is equal to y of 0 plus 2. So I know y of 0 is 6 plus 2, so this would be 8. Now since y prime of 0 equals 8 and c1 happens to equal y prime of 0 over 1 factorial, then we would say that this would then equal 8 over the 1 factorial, which would be 8. So c1 is equal to 8. Now we need to do this for the remaining derivatives, but we're not going to get any different answer for this because y double prime at 0 for this is then going to equal y prime at 0, which is 8, same for y triple prime and the rest. So y to whichever power on this at 0 then equals 8 for k equal to 2, 3, and 4. So let's summarize that. Alright, so this is what we get as our general solution, and we'd kind of like to summarize this and see what this is really equal to. So let's pull the 8 out of here, and I could write that this is 6 plus 8 times the t over the 1 factorial plus t over 2 factorial plus t cubed over 3 factorial plus blah blah blah. Now I can look at this and note that if I had a 1 plus in here, it would really make it nice. So what about if I bust up this 6 and I say that that 6 is actually equal to, how about negative 2 plus 8? And then that way I could get a 1 in here, in which case it would look like, now this is really nice because this guy right here is just my Taylor series approximation for e to the t, so I can say that my general solution is equal to negative 2 plus 8 e to the t. And that was pretty sweet. Let me just go ahead and that equals y of t. Pretty. In our next example, we're looking at finding the approximate value of this integral. If we start off with the Maclaurin series for e to the x, and note that we could replace x with negative x squared, which is what we were looking for, then we can just integrate term by term, and making sure by trial and error that we don't have an error that is greater than this particular value. So let's just start this out, and we're going to integrate 0 e to the minus x squared dx, and we're just going to say that this is equal to the integral of 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus blah 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 dx, and I'm going to integrate this and see what we get. And if you want your error no less than this, what you'll have to do is use n equal to 5, because 1 over 13 times 6 factorial is about 1.07 times 10 to the minus 4, and as long as the error was less than that, then we're good to go. So plugging this in, whoops, we better probably put our limits of integration in here from 0 to 1. And plugging this in, you should get about 0.747 for this integral. In example 6, we're to use the Maclaurin series for inverse tangent to evaluate this particular series. So we go and get the Maclaurin series for that particular function, for that inverse tangent, and we see that when x is 1, when we substitute in here, we get what's sitting there. So let's do that. Alright, so it looks just like our series that we're investigating, and because the tangent inverse of 1 is equal to pi over 4, then we can say that the value of this series is also equal to pi over 4. Alright, we are to look at this particular function where we have f of x is e to the x minus 1 all over x. Alright, so if we use our Maclaurin series, which here it is here, and we substitute that in for e to the x, let's see if we can get an idea of what this thing would look like after we simplify. Alright, in simplifying my terms, I see that this 1 drops. I'm going to pull this 1 over x all the way through, and then I will get 1 plus, multiplying this times that guy, multiplying 1 over x times the x squared will just be x over 2 factorial plus x squared over 3 factorial, and so forth. And in looking at this, I could say that this can be summarized by k equal 1 to infinity of x to the k minus 1 over k factorial. So this converges, negative infinity over infinity. Then we need to use the quotient rule and figure out what f prime of 1 is. Alright, so I got what f prime of 1 is just by doing a straightforward derivative. Next, what I need to do is I'm going to look at the Maclaurin series. I'll take the derivative of each term by term here and see what I happen to get for my f prime of 1 in this way. Alright, there we are, taking the derivative term by term, and if I want to see what this looks like as a series term by term, this would be k plus 1 factorial on bottom, because this is the first term, second term, third term, so that works there. And then there's always a k in front, so that would be k, and then x is to 1 power less, so it would just be x to the k minus 1. And if I evaluate this at x equal 1, you'll notice that this also equals 1. Whoops, I better write that if for f prime of 1. Okay. Alright, if I look at this power series and I try to figure out which one it's most similar to, I choose e to the x, and it converges from negative infinity to infinity. But if I replace x with 1 minus 2x, then what I would get is this sum, k equals 0 to infinity of 1 minus 2 to the x, right, which is exactly what we have. Therefore, I can say that this is e to the 1 minus 2x. And since e to the x converges from negative infinity to positive infinity, we can say we replaced our x with 2x minus 1, and in this case You'll notice if I add 1 to infinity or divide it by 2, it's still negative infinity to positive infinity for that interval of convergence. Well, first up, if I'm wanting to determine the interval of convergence, I'm going to do the ratio test, and when I do this, I'm going to end up with the absolute value of x squared over 4. It's got to be less than 1, and this is going to imply that x is in between negative 2 and 2 would be that interval of convergence, and it is going to diverge at these endpoints, so they would not be included in this. Next, in order to find a function that this represents, we're going to have to do a little simplifying. I'm just going to start pulling out numbers and seeing what it is that I get with this. Alright, now this is really a rig. I'm going to pull out an x, and I'm going to both multiply by 2 and divide by 2 here. I'm going to recognize that this is a derivative. It is derivative of x to the 2k, and then I'm going to have everything in terms of a power of k, so I'm going to be able to squish this together. Alright, so just writing this as the derivative, that right there is equal to this, and then I am just busting that x to the 2k apart so that I can end up squishing this together. And this is pretty cool because we now have a geometric series where my ratio, where my r is equal to negative x squared over 4, and with that first term being negative x squared over 4. Therefore, we can write this down and simplify. Alright, so I can just write this using the fact that this is a geometric series, and I just use the sum of the geometric series. Now I'll take and say that this is that sum, so I'll take the derivative of this and get my function. And this would be my function provided my x is in between negative 2 and 2. And there we have it. Stunning, and it is a pretty good rig here, but that is how we got it. And that concludes this section. If you have any questions, see me at the Collaborate or send me an email.